Hi guys, let's find the mutual inductance of two long solenoids. So here two solenoids which is S1 and S2, they are wounded or they are kept coaxially. It means they are having common axis. If they are having common axis, then we call as coaxial. Okay. Now we need to find the mutual inductance of these two long coaxial solenoids. So we learned about the mutual inductance. Let us try to find the expression for mutual inductance for these two long solenoids. Suppose if I draw a figure again, so let this a solenoid of radius R1 having each turn. So if I take this is a solenoid which I call S1, through this solenoid I1 is amount of current which is flowing through the solenoid S1. If you take the radius of ring or radius of each turn, so the radius of each turn equal to R1 and L is the length of the solenoid. Now in this solenoid, if we can bring one more solenoid, so let this is another solenoid which is wounded over solenoid S1. If I take this is solenoid S2, so through this solenoid current I2 is passing. I can call that current as I2 and the radius of each ring, so this we take as R2. So we need this terminology carefully. So here S1, S2 are two solenoid, and important thing is that one S2 is wound over S1, and apart of that, so L equal to length of each solenoid. L equal to length of each solenoid, and R1 comma R2 is equal to radii of each solenoid, and N1 comma N2, capital N1 comma N2, so these are nothing but number of turns in the two solenoids. And apart of that one, I need one more quantity that equal to A, capital A equal to, if I take pi R1 square, which gives the area of cross section of solenoid S1. So here L is the length of the each solenoid, means remains same, and R1 and R2 are the radii, and N1 and N2 is nothing but number of turns in the solenoid, and A equal to pi R square, which equal to area of cross section of solenoid S1. So after that, suppose if you pass time varying current I2, if we pass time varying current, it means AC current, time varying current I2 in S2. So if we pass time varying current I2 in S2, what happens there? Then because of the current I2 in solenoid S2, there will be magnetic field will set up. The magnetic field will be set up in S2 due to the current I2 only. Yeah, I2 is passing, time varying current is passing through solenoid S2. So we know that a time varying current produces magnetic field. So the magnetic field is producing in S2. So if I write that the magnetic field in S2 due to I2 is, so if you can call that as magnetic field B2 equal to, so the magnitude of magnetic field due to a solenoid, we already derived this expression, that equal to mu naught times small n2 times I2. So here small n2, here the little n2 is equal to small n2, which is equal to capital N2 upon L, which is also called the number of turns per unit length. Number of turns per unit length. So this is the expression for magnitude of the magnetic field due to a solenoid S2. So this expression B2 equal to mu naught times N2 times I2. So here mu naught is permittivity and little n2 small n2 is the number of turns per unit length. Now because of the magnetic field in S2, there is a change in flux. The total magnetic flux change. Magnetic flux linked with the solenoid S1. Yeah, because solenoid S1 is inside the solenoid S2. So the same magnetic flux which is developing in S2, that will be changes through solenoid S1. So if we can write the total magnetic flux pi 1. So this I am writing due to solenoid S1. So we can use the flux pi 1 equal to flux formula B dot A means magnetic field and the area of the coil B dot A, and here the coil having the N1 number of turns. Therefore here the magnetic field is B2, or you remember the flux formula, flux pi equal to B dot A. If the coil having the number of turns, so we need to include the N also. So this is the magnetic flux formula. So here the magnetic field is due to the B2, it is due to the solenoid S2, and A is the area of the coil of S1 obviously. Here N1 equal to number of turns of the coil S1. Now if you can substitute the B1 value at here, so therefore flux pi 1 equal to, in the place of B2 I can put the value mu naught times little n2 times I2 times A times N1. Since here B2 equal to how much it is? Mu naught times N2 times I2. Okay, so this is the flux pi 1, and we know the mutual inductance formula. So the mutual inductance M. So how the mutual inductance comes? Flux is directly proportional to current. So therefore flux equal to M times mutual inductance times current I. So mutual inductance M equal to flux upon current I. Now here we need to be careful. because current is passing in one coil but the flux is changing in the another coil. Therefore, if you can write the mutual inductance, of coil 1 with respect to coil 2, with respect to coil 2 is, so I can write the mutual inductance formula M equal to, capital M equal to phi upon I2. This is the mutual inductance formula. But we need to be careful where is the flux. So for that, if we can write precisely what is this mutual inductance. Mutual inductance of the first coil due to the current in the second coil. So that I can represent as M12, which is equal to the change in flux in the first solenoid because of the change in current in the second solenoid. So because we apply current, change in current, where we applied? So we applied the time varying current in S2 only. So if you apply the time varying current in S2, because of the time varying current which included in the solenoid S1, so there is a change in flux. Now if we can substitute the known values at there, therefore M12 mutual inductance of S1 due to S2 equal to phi naught value I already got it, that is mu naught times N2 times I2 times A times capital N1 upon I2. So let me cut the like terms. So here I2 gets cancelled, I2 gets cancelled. So if you can rewrite the expression M12 equal to mu naught times and N2 times A times N1. I would like to rewrite this expression in terms of capital N2, since we know that little n2 equal to number of turns per unit length. Little n2 equal to number of turns per unit length. So if we can rewrite this expression M12 mutual inductance of first coil due to second coil M12 equal to mu naught times, so capital N2 and capital N1 times area upon L. So here I replace little n2 equal to capital N2 upon L. So this term is very important. We call that number of turns per unit length. So this is the expression I got it. I call this equation A. Later I will make use of this equation. So for a moment let me highlight this equation. So mutual inductance of first coil due to current in the second coil. Now if we prove reverse means, suppose if we take, so in the earlier case, in the beginning case I started with a time varying current, which is passing in the S2. Now as a second case, if I take, if a time varying current which is passing in S1, suppose if you consider a time varying current or alternating current, a time varying current I1 is passing through S1. If time varying current is passing through S1, then because of this what happens? There is a change in the magnetic flux which is linked in the solenoid S2. Okay. So before that if I can write the magnetic flux or the magnetic field, due to I1 in S1. Yeah, because of current is passing in solenoid S1, there should be magnetic field. So the magnetic field, if I can take B1 equal to, we know the solenoid expression mu naught times little n1 times I1. Again, here you can write that as n1 equal to number of turns per unit length, capital N1 upon L. So that I will write it later. Now because of this magnetic field, so the total flux now linked with S2. So because of the current which is passing in S1, there is a magnetic field B1. Now this magnetic field is linked with the another solenoid which is S2. Now because of that change in flux in S2, there is a mutual inductance in S2. That's we want to going to get it. So the total flux linked with S2 equal to the flux phi 2 equal to, so we know the flux formula, flux phi equal to B dot A, and if coil having number of turns, so I can add that B dot A times N. Now here flux phi 2 equal to B dot A times N. Now I want to find the flux due to S2. So obviously the number of turns will becomes N2. Okay, there is no problem here to write N2, and A is the area of the coil. And what is the B at here? So the B is the magnetic field due to coil S1. Why it is? Because we applied the magnetic field to coil S1 only. Sorry, we apply a time varying current I1 to solenoid S1. So now solenoid S1 only contributes magnetic field B1. So now the flux formula changes phi 2 equal to B1 times A times N2. Now you can substitute the B1 value. So B1 value goes to mu naught times little n1 times I1 times A times N2. Now as usual, if you can use this N1 at here, N1 equal to number of turns per unit length. Now the above expression will be changes as flux phi 2 equal to mu naught times capital N1 capital N2 times I1 times A upon L. So this is the flux phi 2. After getting flux, we need to write the mutual inductance. So we can get that mutual inductance. Flux is directly proportional to current I. So flux equal to M times I. Therefore mutual inductance M equal to phi upon I. Now if you can write the mutual inductance, now this time mutual inductance of coil 2 with respect to coil 1. Mutual inductance of coil 2 with respect to coil 1. So this is exactly opposite the case what we are dealing. Now in that case I can get that mutual inductance of coil 2 with respect to coil 1, which equal to the flux in the coil 2 upon current in the coil 1. So we got that the flux expression above. So if you can put that at here, mu naught times n1 n2 I1 times A upon L upon I1. Now if you can cut I1 and I1, now I got this expression M21 equal to mu naught times N1 N2 A upon L. So this is the mutual inductance of coil 2 with respect to coil 1. So if you can call this as expression B, now if you can see this expression A and expression B are similar. So the mutual inductance of first coil with respect to second coil equal to mu naught times capital N1 N2 A times L. The same expression, the mutual inductance of coil 2 with respect to coil 1 equal to mu naught times N1 N2 upon A upon L. So therefore, we got the conclusion that mutual inductance of second coil with respect to first coil is equal to mutual inductance of first coil with respect to second coil. So they both are equal. Suppose if I call this as M itself for two solenoids. So let a case, if M12 equal to M21 equal to M, then I can write mutual inductance of two solenoid formula M equal to, so mu naught times capital N1 and capital N2 A upon L. So this is the expression for mutual inductance of two solenoids. Now let's do little further more simplification for the better understanding. So instead of writing N1 N2 number of turns, so we would like to write in terms of little n1 comma little n2. So here little n1 equal to the total number of turns per unit length, and little n2 equal to the total number of turns per unit length. So if you can, if you want to rewrite this expression like this, so the above expression will be changes as, so capital M, mutual inductance capital M equal to mu naught times little n1 and little n2 times A times L. Yeah, because of this n1 upon L, little n1 upon L, I can put the value of n1, so this value I can substitute it. And for the capital N2, so from here if you can rewrite capital N2 equal to small n2 times L. So if you can substitute capital N2 plus small n2 times L, so we got that mutual inductance M equal to mu naught times N1 N2 A times L. I would like to write further more clearly. So M equal to mu naught times N1 and N2 A is equal to pi r square times L. Here R1 means R1 equal to radius of the or area of cross section of inner solenoid. So this expression gives a very important conclusion that the mutual inductance of solenoid is purely depends upon the geometrical structure of the solenoid. What is it meaning of the geometrical structure? So it's purely depends upon the length of the solenoid. How much length is there? The mutual inductance is directly proportional to length, and it is also directly proportional to area of cross section of each turn. And not only that, it is directly proportional to the number of turns per unit length, and above that it is the permeability. So the mutual inductance is independent of the amount of current which is flowing. So in the above expression, we do not find anywhere the factor of current It's purely depend upon the geometrical structure of the solenoid. So the factors on which mutual inductance depends. Factors on which mutual inductance depends. So this is a very important concept. So first one goes to number of turns. Yeah, mutual inductance is directly proportional to N1 and N2. So in the two solenoids, number of turns are the more, or in this case precisely you can say number of turns per unit length, or this expression also you can write that mutual inductance directly proportional to capital N1, capital N2. So if number of turns are more, then the mutual inductance of the two solenoid will equal to increases. And the second one is directly proportional to the mutual inductance is depends upon the common cross-sectional area. So mutual inductance is depends upon common cross-sectional area. So the larger the common cross-sectional area of the two solenoids, then the larger will be the mutual inductance, because you are seeing it here, mutual inductance is directly proportional to pi r1 square. Why it is the common cross-sectional? Because the r1 is only the radii of inner solenoid and r2 is the radii of the outer solenoid. So for the inner and outer, the common cross-sectional only r1. So that's why the mutual inductance is directly proportional to common cross-sectional area. And the mutual inductance is also depends upon the relative separation, how much far they are. So it is also depends upon relative separation. If the two coils are too close, then the mutual inductance will be increases. And it is also as a factor of relative orientation. So what does it mean? So these two are not included in the formula. So these are the external factors. It means if we know the magnetic field, how it will be changes. If the coil is S1 is like this, and if the coil S2 is perpendicular like this. So if this is S1 and this is S2, the magnetic flux linked with the coils. So the magnetic flux which is linked with the coil in these two cases are different. So that's why the relative orientation of the two coils also increases the mutual inductance. And not only that, the relative separation. If the two coils are too far, means they have certain measurable gap, then the mutual inductance will be decreases. So these two factors are not included in the formula, but these are the geometrical structure factors. And above that, the mutual inductance is directly proportional to permeability. Permeability mu naught of the core material. So because M is directly proportional to mu naught. So we know that different magnetic materials are having different different permeability. So if we insert a magnetic material which is having more permeability, then the mutual inductance is also increases. So these are the factors which are affecting the mutual inductance of two solenoids. The final expression for the mutual inductance of two solenoids M equal to mu naught times N1 N2 pi R square times L. So I hope you practice this expression carefully.